Hey guys, this is Harold L.R. Watkins back with another demonstration. In this demonstration, I will be demonstrating Quadtree Spatial Index. This is the Quadtree Spatial Index I built for my efficient analyze ride sharing simulator. It finds the nearest available driver without scanning their entire fleet. A brute force search takes big O of n time, while a balanced quadtree averages approximately big O of log n for distributed points. In quadtree.py, um, we can filter. That's probably the easiest way. Um, well, the classes are easier to find than everything else. So, okay. So the classes that we are mainly working with is point, rectangle, and quadtree node, as you see here. Um, the point class stores a location in driver identifier. Rectangle defines a map region and calculates boundary distance, while quadtree node stores points in up to 4 child regions. Quadtree is the public wrapper that creates the root node and exposes insertion in nearest neighbor search. Moving to insert and subdivide. This is going to be in test quadtree.py. And here we will focus on uh, insert, which we should be defining. What's that? Um, we have I'm gonna end up filtering for this insert. Let's filter for it. So in Quadtree, I'm in the wrong one. That's what it is. I'm supposed to be in Quadtree.py, which is here. And we're supposed to be focusing on inserts. Have the children, and we have insert. Awesome. All right. So insertion first rejects a point outside the current boundary. If the node is a leaf with room, it stores the point locally. Each leaf holds up to 4 points, and the maximum depth safeguard prevents endless subdivision at duplicate coordinates. So here we would see you have your insert and your point, find nearest, and insert. Moving to subdivide. When a leaf reaches capacity, subdivide creates um, northwest, northeast, southwest, and southeast child regions. The node redistributes its existing points, then recursively inserts the new point into the uh, correct child. This builds the spatial hierarchy automatically. Then moving to um, find nearest. There's also filter for, there we go. Don't have to filter for it. Find nearest. The nearest neighbor search carries forward the closest driver found so far. And that driver squared distance from the writer. Square distance avoids an unnecessary square root calculation during each comparison. Moving to find nearest inside find nearest, as to say. The if self dot boundary, which we should see here. Boom. This condition is the key optimization. If the closest possible location inside a region is already further away than the best driver found, the method skips that node and every child beneath it. The search therefore avoids work that cannot improve the answer. That's what you have there. Then moving to promising regions, which is still inside find nearest. Um, self point, it should be, looks like I'm window filtering for this. Um, all right, let's filter this. So, oh, that's what I'm saying for. Okay, um, for a viable region, the method checks is stored points and updates the best route. It then sorts child regions by boundary distance and searches the closest one first. And an early close match makes the pruning test more effective on the remaining branches. Moving to verification, standalone verification. You're gonna open test quad.py, which is here, and we're gonna focus on number of points. So this is number, there you go, number of points. What am I doing? No. Um, the standalone test inserts 5,000 reproducible driver locations. It sends the same rider location through the Quadtree and brute force searches, then asserts that both return the exact same point object. Additional queries and edge cases provide broader correctness coverage. So additional queries and edge cases provide broader correctness coverage. Then moving to demonstrate the result. Let's open up. I already ran the program, but we can run it again. So let me grab my folder and run this application. So I am going to close this and I'm going to rerun it. Let's do that. Open up this. All right. So it's larger. Okay. Both methods found the same driver. Give it a moment. I got ahead of myself. All right. Both methods found the same driver at the same distance. Results identical is true, and all Quadtree correctness checks passed. The measured timing can vary by a computer, but the assertion guarantees that the optimized search matches the brute force result. What you can see here, the tested Quadtree is ready for the simulator final driver matching workflow, replacing a full fleet scan with reusable recursion search and spatial pruning. And with that, that pretty much covers my demonstration of Quadtree Spatial Index. Um, see if I'm missing anything. This one was quite technical, so I did my best to try to uh, articulate it in a way that non-technical people can relate or understand it. Um, yeah, this was a deep project. That's all I can say. This wasn't an easy one. And with that, thank you for watching.